Well, at the end of the previous lecture, we proved the half exactness of the functor k0. So let's recall the statement of this result. Suppose we have a ring extension of the following form. A ring extension. This means that essentially this means that we have a surjective ring homomorphism of R onto S, such that I is the kernel of P. So I is a two-sided ideal of R, and S can be identified with the quotient of R modulo I. So this is a ring extension. And we proved the following theorem, which states that for every ring extension of this form, it induces an exact sequence of k0 groups of the following form: k0 of I, k0 of R, and k0 of S. This sequence is exact. And this property is called the half exactness. Of k0. So now the initial question is, how about the exactness? Or at least left or right exactness? In other words, what if we put 0 to the left of k0i and extend this sequence in this form? Will it be exact? And similarly, what if we add 0 here? In general, the answers to both questions are no. Let's look at some examples which illustrate this phenomenon. Some examples which show that in general, k0 is neither left exact nor right exact. Well, suppose we have a compact Hausdorff topological space X, and Y is a closed subset of X. And let U denote the complement X minus Y, so U is open. It's a simple exercise to show that if we take the ideal in C of X consisting of those functions which vanish at Y, such that the restriction of F to Y is 0, then this ideal is actually isomorphic to C0 of Y, the algebra of continuous and vanishing at infinity functions on U, C0 of U, sorry. And in fact, the isomorphism is quite explicit. It takes every F to its restriction 2. And so we have an extension of the following form. C0 of U becomes an ideal in C of X, and the quotient is C of Y. Here we have the restriction map, which is, of course, surjective by the Tits extension theorem. So by the half exactness of k0, this extension induces an exact sequence of k0 groups, k0 of C0 of Y, k0 of C of X, and k0 of C of Y. Let's now recall that by the Serre-Swan theorem, the k0 groups here are actually isomorphic to the topological k0 groups. So this can be identified with k0 of U. This one is k0 of X. And this one is k0 of Y. So we are interested in this sequence more exactly, we are interested in what will happen. What happens if we add 0 here or here? Let's consider the following two concrete cases. Case 1. Let X be the three-dimensional ball, B3, in R3, closed ball. And Y is the boundary, that is the sphere, S2. How about K0 groups of these spaces? Here we will use the following standard facts. Fact 1 is that K0 of the closed ball, Bn, for every n, is isomorphic to the integers. And this is actually a very simple fact. Probably we'll be able to prove it today by using the homotopy invariance of K0 in the context of C-star algebra, of Banach algebras. And the second fact, which is not so simple, is that K0 of the sphere, Sn, is isomorphic to Z plus Z if n is even, and it is isomorphic to Z if n is odd. This will be proved later on as a consequence of the Bott periodicity theorem. So now if we look again at the sequence in this concrete case, we see the following. Our sequence star becomes the following one, so K0 of u. And at this point, we don't even need to know what K0 of u is. Actually, we could easily calculate it, but this is not necessary now. Here we have Z, and here we have Z plus Z. And it's clear that this map is not surjective. This one is not surjective. There is no surjective group homomorphism from Z onto Z plus Z. So as a result, we see that if we add 0 to the right of the sequence, the resulting sequence is not exact. And so K0 is not right exact. How about the left exactness? Let's now consider a slightly different case. This is example 2. Let's suppose now that X is the two-dimensional ball, which is just the disk. So Y is the boundary of the disk, which is the circle. Here we also want to calculate K0 of u explicitly. So U is the open disk. It is not compact, so to calculate K0 we must take the one-point compactification, U plus. Well, the one-point compactification of the disk is a sphere, S2. And K0 of u, let's recall that for non-compact, locally compact spaces, K0 is defined to be the kernel of the canonical map from K0 of u plus to K0 of the point, which is actually isomorphic to the integers. And the respective map is just the dimension. It takes every vector bundle, every class, the class of every vector bundle to the dimension of the fiber over this point. But U plus is of course connected, so the dimension of fiber doesn't depend on the point. So this is Z plus Z, because this is a sphere, the two-dimensional sphere. of course, this map is surjective. Actually, we can describe it explicitly in terms of generators of z plus z. But anyway, actually, we don't need the explicit form of this homomorphism here, because it's a simple algebraic exercise to show that the kernel of any surjective homomorphism of this group onto this one is isomorphic to z. So in summary, we see that our sequence star now has the following form. It becomes the following sequence. Here we have z. Here we have z again. And here we have z again. So this is k0 of the ball, of the disk actually, and this is k0 of the circle. If I identify these k0 groups with the integers, it's easily seen that this map is just the identity map. So both groups are spanned by the trivial one-dimensional bundle, and it goes to itself under this map. So after identifying with the integers, we see that this is just the identity map. How about this map? Well, the sequence has to be exact in the middle. So the only possibility for this error is that it is 0. Otherwise, it is not exact. But of course, this map is not injective. This map is not injective. And so as a result, we deduce that k0 is not left exact. By the way, another example showing that k0 is not left exact is contained in our second exercise sheet. Okay, it turns out that there is an important special case of extensions for which k0 is exact. And the respective property is called the split exactness of k0. So we have the following definition. Suppose that we have a ring extension of the following form. I, R, and S. We say that this extension splits, or sometimes we say that it is a split extension. So the word split here can be used either as a verb or as an adjective. If the surjective homomorphism P is not just surjective, but is a retraction in the category of rings. If P is a retraction in the category of rings. So explicitly, this means that there is a ring homomorphism J, which acts in the opposite direction from S to R, such that Pj is the identity map of S. So J is just a section of P. Of course, similarly, we can define split extensions in, for example, in the category of algebras or in the category of sister algebras. Extensions in, for example, in the category of K algebras, in the category of sister algebras, and so on, or in the category of Banach algebras. We just require P to be a retraction in the respective category. Let's observe that if our extension splits, if the extension splits, if we forget about multiplication on R, we see that the abelian group, the underlying abelian group of R, is just the direct sum of I and S, because the respective sequence of abelian group splits. So it is isomorphic to the direct sum sequence. And R is isomorphic to I plus S as an abelian group. But in general, not as a ring. Actually, I is an ideal of R, but S is not necessarily an ideal, it is a subalgebra. A subalgebra of R. Actually, we simply identify S with its image under the map J, little j. So little j embeds S onto a subalgebra of R. Sometimes the situation is described as, we say that R is a semi-direct product, or a semi-direct sum. A semi-direct product of I and S. Let's look at some examples of extensions which split and which don't split. Actually, we have already discussed a simple example of a split extension, namely for every ring R, we can consider the unitization extension, which embeds R into its unitization and then projects onto the integers. And we have already discussed that this extension splits, that is, this projection of R plus onto Z is a retraction. In fact, this example can easily be generalized as follows. Suppose that R is a unital, or better A. A is a unital K algebra over any field, or actually any commutative ring K. And suppose that there exists a unital K algebra homomorphism, that's denoted by epsilon, from A onto K. So I claim that the respective extension, we take the kernel of epsilon, embed it into A, and then project by epsilon onto K. This is a split extension. And moreover, it splits in the category of K algebras. Well, indeed, it happens more or less for the same reason that the unitization extension splits. Namely, we can consider the standard structure map, that's denoted by eta, from K to A, which is actually already implicitly or explicitly contained in the definition of a K algebra. And it takes every lambda in K to lambda 1 in A, where 1 is the identity of A. And this is a K algebra homomorphism, and it's a section of epsilon. And so this argument shows that our extensions, first of all, it shows that epsilon is surjective, and actually epsilon is a retraction in the category of K algebras, so the extension splits. In the special case where where K is the integers and A is the unitization of a ring R, and epsilon is the canonical map from R plus to Z, we get example 1. So example 1 becomes a special case of example 2. Okay, so these extensions are split, but on the other hand, it's very easy to produce extensions which don't split. And here's the simplest, probably the simplest example. So it's obvious that this extension doesn't split. actually it doesn't split already in the category of abelian groups. Even in the category of abelian groups. For the simple reason that the only group homomorphism from this group to this one is identically 0. So it is never an embedding. Another simple example of a non-split extension, now in the category of K algebras. Let's take a polynomial f, for example, with complex coefficients of degree at least 2, and consider the following extension of complex algebras. So we consider the principal ideal in the polynomials generated by f, and the quotient modulo over this ideal. And it's a simple exercise to show that this extension doesn't split. A simple exercise in algebra. However, of course, it's easily seen that it splits in the category of abelian groups and even in the category of vector spaces. It splits in the category of vector spaces. For the simple reason that this one is, well, any sequence of vector spaces splits actually. Any short exact sequence of vector spaces splits. One more example, which is, by the way, quite general and which is closely connected to these examples, which we considered at the beginning of the lecture. Suppose that X is a compact Hausdorff topological space, and Y is a closed subset of X. And let U denote the complement of Y, so U is open. So let's look at the extension that we've already considered today, namely C0 of Y is embedded as an ideal into C of X, and the quotient is isomorphic to C of Y. So, by the way, this is a simple but useful exercise to show that this extension splits in the category of algebras. It's natural to consider it in the category of algebras, even only if it splits in the category of C-star algebras. In the category of C-star algebras. And this happens if and only if Y is a retract of X. That is, this means that there is a projection, a continuous map P of X onto Y, which is the identity on Y. Of course, this is closely related to the Gelfand-Naimark theorem, but not immediately, because in general, if we come back to our definition, J is not assumed to be unital here. Even if if R and S are unital, we don't require J to be unital. So there is a little problem to using the Gelfand-Naimark theorem here, but this can easily be solved. Okay, and another example closely related to this one. What happens if X is no longer compact, but is only locally compact? Well, here is a special case of this situation. Let's look at the following extension. We have the algebra C0 of C0 functions on the half-closed interval from 0 to 1. It contains an ideal isomorphic to the algebra of C0 functions on the open interval 0, 1. And the quotient is just the complex numbers. More exactly, if we take the evaluation map at 0 here to the complex numbers, we get an extension of rings, actually of C-star algebras. It looks similar to this one, and y is just a point, actually. But the half interval is not compact, and in fact, this extension doesn't split. This is also a simple exercise. So the compactness of X in the previous example is essential. Okay, now we have the following result, which is usually called the split exactness. Split exactness of K0. Suppose we have a split extension of rings I, R, and S. This is little I, and this is P. I claim that this extension induces the following split exact sequence of abelian groups: 0, K0 of I, K0 of R, K0 of S, and 0. And the sequence is split exact in the category of abelian groups. Okay, let's prove this result. First of all, it's very easy to observe that this sequence is exact at K0R and at K0S. First of all, P is a retraction in the category of rings. P is a retraction in the category of rings. And any functor takes retractions to retractions, so P star is a retraction in the category of abelian groups. In particular, it is surjective. It is surjective. And we see that our sequence is exact. The sequence is exact at, first of all, at K0 of R, just by the half exactness of K0. And at K0 of S, by the surjectivity of P star. So what is not entirely obvious is that I star is injective. So to complete the proof, we must show that I star is injective. Then our sequence will be exact. And since P star is a co-retraction, we will deduce that it is split exact. Well, so we want to show that the kernel of I star is true. Let's take an element, little x, in the kernel of I star. So it is contained in K0 of I. And if you now recall the standard picture of K0 of I, the standard description of K0 of I in terms of idempotence, we see that X can be represented as the difference of two classes of idempotence, E minus 1n. Let's call that 1n denotes the identity in the n by n matrix algebra. Oh, by the way, yes. Yes, we proved this some time ago, that K0 of I consists of all elements of this form, where this is the identity in the n by n matrix algebra over I plus, of course, standardly embedded in a standard way in the infinite matrix ring. So epsilon is an idempotent in M infinity of I plus, and such that E minus 1n sits not only in M infinity of I plus, but actually in M infinity of I. So this was our standard description of K0 of a non-necessarily unital ring. Well, since I star of x is 0, so this condition means exactly that if we identify little I with its image in R, which is more or less standard convention, we see that the respective elements, this one and this one, are equal in K0 of R plus. Well, I star on the level of K0 groups is just a restriction of the similar I star on the level of their unitizations. So the difference of these elements goes to 0 if and only if these elements are the same in K0 of R plus. Formally, this means that the respective idempotents are stably equivalent, or equivalently stably similar. But we can use a standard trick, which we have already used at least twice, and assume that these idempotents are actually similar. We may assume that E and 1n are similar in mk of R plus for some k greater than or equal to n. Let's recall how this works. Otherwise, if they are not similar but only stably similar, we simply replace E by E plus 1L for suitable L and 1n by 1n plus L, so that the resulting elements will be similar, but this difference here will be the same, so x will be the same. So by changing these elements, we may assume from the very beginning that they are similar. Okay, so what we want to show? We want to show that actually they are similar not only in here, but already in mk of I plus. That these two elements are the same in K0 of I plus. Okay, so they are similar, so we can find an invertible matrix. Choose an invertible matrix V in GLK of R plus, such that this matrix conjugates these two elements, so V inverse equals 1n. So our strategy will be to modify V in such a way that it becomes an element of GLK of I plus. Somehow we want to project it onto I plus. How can we do it? Well, let's consider the following element, as denoted by U, given by the following formula. G plus P plus applied to V inverse and then multiplied by V. So in other words, we project V inverse onto, oh, I forgot to say what J is, where J is a section of P from S to R. This is the right inverse to P. Of course, here we use the assumption that the extension splits. So we project V inverse onto S, then move it back to R by J plus, and multiply it by V. So this is a multiplicative version of a very standard trick of working with exact sequences. The only difference is that we are using the multiplicative structure. So what can we say about this U? Of course, it is still invertible. It is an element of GLK of R plus. But it has the advantage that if we project it onto S plus, then we get P plus of U is P plus J plus P plus applied to the inverse times P plus of V. So P plus J plus is the identity map. And P is a homomorphism, so we get the identity in GLK of S plus. So this is the identity matrix. Sorry, 1K, of course, 1K. This implies that the element U minus 1K belongs to the kernel of P plus. So what do you know about the kernel of P plus? Here P plus is considered at the level of K by K matrices. Actually, we know that this is nothing but MK of I. Well, why is it so? We have already discussed this argument at the previous lecture. Let's recall that this is true because our original sequence of abelian groups is exact. If we add identities to R and S, it is still exact. And if we consider the matrices now of arbitrary size, then the resulting sequence is also exact. So we see that the kernel of P plus acting at K by K matrices is just MKOA. Okay, so this element sits in MK of I. How about U? Well, U, then since 1K is just the matrix where we have K identities on the diagonal and infinitely many zeros. So this implies that U is actually an element of GLK of I plus. It has coefficients in I plus. Now to complete the proof, we have to show that U gives us similarity between these two elements over I plus. Well, let's calculate U inverse. U inverse. So U is J plus P plus applied to V inverse times V. This is U. Then we have E, and then U inverse is V inverse multiplied by J plus P plus applied to V. Okay. Now V inverse is 1n, this standard projection onto the n, onto the matrix, the respective matrix with n identities and many zeros. And this is, of course, equal to J plus P plus applied to 1n. And since J plus P plus is an algebra homomorphism, we deduce that this is J plus P plus applied to V inverse 1n V. V inverse 1n V is, we'll look again here, we see that this is E. J plus P plus applied to E. And now we do a little trick and represent this element E as in the following form. This is E minus 1n plus 1n. Why is it useful? It is useful because E minus 1n has coefficients in I. Just look here. So it has coefficients in I. And so when we apply P plus to this difference, it goes to 0, again by this exact sequence. So it is in mk of I, which is equal to the kernel of P plus. So after we apply P plus to this element, we get 0, and as a result, we get J plus P plus applied to 1n, which is just 1n. Okay, so we see that E and 1n are similar, but now as matrices over I plus. So U is similar to sorry, not U. E is similar to 1n in mk of I plus. And therefore, the respective elements of K0 are the same. In K0 of I plus. And so we conclude that our original element with X is 0. And this completes the proof. So we have proved that I star is injective. Therefore, our resulting sequence is split exact. Here is a useful corollary. Actually, I have already announced this corollary at the previous lecture. The corollary states that if we work not with just rings but with K algebras, then we can define K0 of a non-unital K algebra entirely in the setting of K algebras. In other words, we can replace the ring unitization by the K algebra unitization. So more exactly, we have the following result. Suppose that R is a K algebra, or K is a commutative ring. And let R plus K denote the K unitization of R. That is, R plus K is the direct sum of R and the free modulo of rank 1 spanned by a single element 1 plus with obvious multiplication. So the multiplication is defined in the same way as in the case of ring unitization. So we have a canonical map epsilon k, which takes the K unitization onto K. Explicitly, it takes every element of the form A plus lambda 1 plus 2 lambda. And we already know that the respective extension splits. So R is contained in R plus K. This is projected onto K. So this extension splits. And so by the split exactness of K0, we deduce that K0 of R is isomorphic to the kernel of the induced map epsilon K star of the respective K0 groups. So in other words, we can replace the ring unitization by the K unitization of R and get the same group K0 of R, which is quite useful. Okay, that's all I wanted to tell you about K0 in the pure algebraic setting. Now we come back to functional analysis, and our next goal will be to discuss an important property of homotopy invariance of K0. Homotopy invariance of K0 for Banach algebras. As a first step towards this goal, we will introduce another equivalence relation for idempotence over a Banach algebra. Well, first of all, let's recall some equivalence relations, actually two equivalence relations for idempotence that we already know about. Suppose that R is a unital ring. Then we have two equivalence relations on the set of idempotence in R. The first one is denoted like this, and is called the algebraic equivalence of idempotence. Algebraic equivalence. And similarity, denoted like this. And let's recall how they are related. We know that if two idempotents are similar, then they are algebraically equivalent. And we know that in general the converse is not true. There are simple counterexamples. But on the other hand, the converse is true if we pass two 2x2 matrices. In other words, if E and F are algebraically equivalent over R, then the respective idempotence will be similar in 2x2 matrices in M2 of R. Hence, if we replace R by the ring of infinite matrices, then the respective relations, algebraic equivalence and similarity, are the same on the set of idempotents in M infinity of R. Of course, this ring M infinity of R is not unital, even if R is unital. But here we follow the convention that two matrices in this ring are said to be similar if they are similar in Mn of R for a suitable n. Okay, so this is what we know about equivalence relations for idempotence. And now we introduce another equivalence relation, which makes sense in the setting of not arbitrary rings, but in the setting of Banach algebras. We start with a purely topological definition. Suppose that X is a topological space. And suppose we have 2 points, x0 and x1 in the space. We say that they are homotopic if they can be connected by a continuous path. That is, if there exists a continuous map gamma from the closed interval 0, 1 to X, which connects x0 to x1 in the following sense. Equivalently, this property means that x0 and x1 belong to the same path-connected component. x0, x1 are in the same path-connected component of X. Well, the following example clarifies a relation actually an example and an exercise at the same time. It clarifies the relation between homotopy in this sense and the more common notion of homotopy for continuous maps. Suppose that Y is a compact Hausdorff topological space. And suppose that we have a subset Z of a normed space E. E is a normed space. And we'll let X denote this space of continuous maps from Y to Z. We topologize X in the following way. We equip X with the topology induced from the space of continuous functions from Y to E. And the topology in this space is given by the standard supremum norm. So X becomes a topological space, actually a metric space. So now the exercise is to prove that two maps F0, F1, 2 points of X, that is two maps from Y to Z, are homotopic in the sense of this definition. Even only if they are homotopy as maps from Y to Z. They are homotopy as maps from Y to Z, which means that there exists a continuous map big F from the product of Y by the interval from the cylinder over Y to Z, such that the restriction of big F to the basis of the cylinder are F0 and F1 respectively. That is, we have the following equations. This is F0 of Y, and Fy1 is F1 of Y for every little Y. Okay, now we will be interested in this notion in the case where X is the set of idempotents in a Banach algebra. So from now on, we assume that A is a unital Banach algebra. For technical reasons, it will be convenient to introduce one more equivalence relation on the set of idempotents in A. If we have two idempotents, E and F, in A, we say that they are semiotopic. And we will use the following notation, SH. So the notation suggests that this relation will somehow combine similarity with homotopy. So they are semiotopic if there exists a path, a continuous map U in a path in the set of invertibles of A cross, which takes T to an invertible event UT, such that U0 is the identity of our algebra, and U1 generates a similarity between E and F. It's a simple exercise to show that this is indeed an equivalence relation. This is an equivalence relation on the set of idempotents. We simply multiply to prove the transitivity, we must simply multiply to continuous paths pointwise. And it's clear, let's observe that if two elements E and F are similotopic, then they are similar. This is clear because of this. And at the same time, they are homotopic. To construct a continuous path from E to F, we just take, we define a path by the following simple formula: ut, E, ut inverse. And this will be a continuous path which connects E to F. We now have the following useful lemma, which states that nearby idempotents are necessarily semiotopic. More exactly, you have two idempotents, E and F, such that the distance between them is small enough, namely it is strictly smaller than 1 over the norm of 2E minus 1, then they are semiotopic. To prove the lemma, we consider the following element, that is denoted by U, given by the following formula: 1 minus E minus F plus 2EF. Just a little algebraic trick. So what can you say about this element? I claim that it is invertible. To prove that it is invertible, let's look at 1 minus U. So this is E plus F minus 2EF. So now the trick is to replace E by 2E squared minus E. Of course, this is equal to E because E is idempotent, plus F minus 2EF. And now we simplify this as follows. We combine these two together, and their difference is 2E times E minus F minus E minus F. And so, as a result, we get 2E minus 1 multiplied by E minus F. And now look at our condition. So this condition and the submultiplicity of the norm readily implies that the norm of this element is less than 1. So this implies that the norm of 1 minus U is strictly less than 1. That is, U sits in the open bowl of radius 1 centered at the identity. Let's denote this bowl like this. The open bowl of radius 1 centered at the identity of the algebra. And let's now recall one of the most basic results in Banach algebra theory, which states that this bowl consists entirely of invertibles. So we know that this bowl is contained in A cross. It consists of invertibles. So U is invertible. And let's also observe that if we multiply U by E on the left, consider EU, what we get, E minus E, they cancel, minus EF plus 2EF. So the result will be just EF. And the same result, we get the same result if we multiply u by f on the right. Again, if we multiply it by f on the right, we get f minus f, they cancel, minus ef plus 2f. Again, we get ef. But now, since u is invertible, we deduce that u f u inverse equals e. So e and f are similar. We want something more. We want to show that they are not just similar, but they are semiotopic. But since u sits in this ball, and this ball is of course a convex set, we can simply connect u with the identity just by a straight line. So let ut denote the following convex combination: tu plus minus 1 minus t times 1. So this is a convex combination of two elements of the same ball. So the ball is convex, and so this is in the same ball, which consists of invertibles. So ut is invertible. Clearly u0 is 1, and u1 is u. And we also know that u1, that is u, gives us a similarity between f and e. And as a result, we deduce that e and f are semiotopic. And this completes the proof. As a corollary, we deduce that the set of idempotents in A is locally path connected, which means that for every point E in this space, and for every neighborhood U of E, every neighborhood contains a smaller path-connected neighborhood. There is a path connected V containing E and contained in U. And it's a standard fact of general topology, which is quite simple, that this property of a topological space implies that if you have a locally path-connected topological space, then its connected components are the same as its path-connected components. Hence, the connected components of the space are identical to its path-connected components. We now have the following useful result. A theorem: if we have two idempotents E and F in A, then they are homotopic, even only if they are semiotopic. So actually, we see that our recurrent installation is auxiliary because it coincides with the homotopy relation. In particular, this implies that if two elements are homotopic, then they are similar. Two homotopic idempotents are similar. And the proof is very easy, modulo the previous lemma. Well, indeed, let's suppose that, of course, we have to show that if they are homotopic, then they are semiotopic. So suppose they are homotopic. And let's choose a path. A continuous path, gamma of idempotents, which connects E and F. And by using this path, we introduce an equivalence relation on the interval. We define an equivalence relation on 0, 1. As follows, we say that 2 points S and T are equivalent if the respective idempotents gamma of S and gamma of T are semiotopic. Well, clearly this is an equivalence relation. And our lemma readily implies that the equivalence classes are open. Are open subsets of the interval. Because if we fix little t, and if S is close enough to T, then by continuity of gamma, gamma of S will be close to gamma of T, and we can achieve that this gamma of S will be in the respective ball of this radius around E, but then they will be semiotopic. And so equivalence classes are open, but the interval is connected, and so we have only one equivalence class. So every 2 points are equivalent. And of course, by applying this to 0 and 1, we deduce that E and F are semiotopic. And this completes the proof. Okay, so now we know that we have 3 equivalence relations. We can forget about semiotopy because it is the same as homotopy. We have three equivalence relations on idempotents, namely homotopy, similarity, and algebraic equivalence. We know that homotopy implies similarity, and similarity implies algebraic equivalence. And the initial question is, maybe homotopy and similarity are actually the same. In general, the answer is no. So it's a fact that in general, if two idempotents are similar, this doesn't imply that they are homotopic. And we will give the respective example later on after we discuss the Bott periodicity. Nevertheless, the situation with these two equivalence relations are about the same as between algebraic equivalence and similarity. Namely, if two idempotents are similar, then they become homotopic in 2x2 matrices. So we have the following result. If we have two idempotents E and F, if they are similar, then they are homotopic, or more exactly E plus 0 and F plus 0 are homotopic as idempotents in 2x2 matrices, M2 of A. Well, actually, I'm slightly cheating here because so far I didn't explain why M2 of A is a Banach algebra. In fact, it is a Banach algebra. Here's a little remark. If we take Mn of A, well, we know that this is a C-star algebra if A is a C-star algebra. But now we are working with Banach algebras. But we can easily make this algebra into a Banach algebra by identifying it with the algebra of endomorphisms of the free module Am. So this is, in turn, this is a subalgebra in the algebra of bounded linear operators of An, where An is equipped with a suitable norm. For example, with the norm given by the following simple formula. The norm of an element A1 to An is just the maximum of the norms of the coordinates. So every endomorphism of an is clearly continuous or bounded because it is just given by multiplication by a matrix. Right multiplication by a matrix. So we have this isomorphism, and it's a simple exercise to show that this is a closed subalgebra. This is the closed subalgebra of B of an. And so it is a Banach algebra. It is a Banach algebra. Okay. So now our theorem, at least, it makes sense. So M2A is also Banach algebra. And the proof will be based on the following simple but useful lemma, which is actually a version of Whitehead's lemma. And now we have already used another version of Whitehead's lemma. This is a very close result. Suppose that we have two elements, two invertible elements, x and y, of A. So I claim that the following matrices, x, y plus 1, x plus y, y plus x, yx plus 1, what else? 1 plus xy, and 1 plus yx. They are homotopic. In GL2 of A. The proof is based on the following trick. We consider the following 2x2 matrix that's denoted by ut, so it depends on a parameter t, which is between 0 and 1. And ut is the following 2x2 matrix. So geometrically, this is a rotation by a suitable angle. So clearly, this is invertible 2x2 matrix. Its inverse is just, to get the inverse, we just take the transpose. And if we now consider the following path, which takes t to the product of x plus 1, ut, y plus 1, ut inverse. Clearly, this is a continuous path of in GL2 of A. And this is a path which connects x, y plus 1 and x plus y. A little exercise is to perform the respective calculation. It's clear that if t is 0, then this is just the identity matrix. And so we just get the product of x plus 1 and y plus 1, which is xy plus 1. And if t equals 1, then we multiply these matrices in a straightforward way, and we get x plus y. So these two elements are homotopic. And it's also a simple exercise to show that x plus y and y plus x are also homotopic. A hint is to consider the permutation matrix, which gives us similarity between these two, and connect it to the identity matrix by a suitable continuous path, which is quite similar to this one. Not identical, but very similar. Basically, this is the end of the proof, because now we know that these two are homotopic, these two are homotopic. So since these are homotopic, we see that these two are also homotopic, and since we can interchange x and y, we deduce that these two are also homotopic to the previous matrices. By using this lemma, we can now easily prove our theorem. Indeed, let's take an element, invertible element U, which gives us a similarity between E and F, such that U inverse equals F. And apply Whitehead's lemma to U plus U inverse. So the lemma implies that U plus U inverse is homotopic to the identity matrix in GL2A. We simply apply this lemma in the setting where X is U and Y is U inverse. Well, they are homotopic, so let's take a path. So I'll take a path which takes T to WT in GL2 of A, such that W0 is the identity matrix and W1 is U plus U inverse. And now consider a path which connects these two idempotents. We define a new path which takes T to the element ET, given by WT, E plus 0, WT inverse in the set of idempotents of 2 by 2 matrices. And it's clear that if T equals 0, then we get, so W0 is 1, so we get just E plus 0. And if T equals 1, what is W1? We multiply U plus U inverse times E plus 0 times U inverse plus U. So we multiply 3 2 by 2 block matrices, and of course we get F plus 0. And so they are homotopic. And this completes the proof. So in conclusion, what happens if we pass to infinite matrices? We can easily extend the notion of homotopy to infinite matrices as follows. You have two idempotents E and F in M infinity of A. M infinity of A is not a Banach algebra, of course. But it is a directed union of matrix algebras which are Banach algebras. And we say that E and F are homotopic. Or respectively semiotopic. If they have this property in Mn of A for a suitable n. If they have this property in Mn of A for some n. Then now combining our results, we obtain the following corollary. For any unital Banach algebra, the algebraic equivalence, similarity, the homotopy, and the semiotopy are the same on the set of idempotents in M infinity of A. So all four equivalence relations become the same if we enlarge A to the ring of infinite matrices. And as a result, we can define K0A as follows. We take the idempotents in M infinity of A. We factorize by any of these relations because they are the same. And we take the Grothendieck group of this semigroup. Okay, so by using this property, we can easily prove, we could easily prove the homotopy invariance of K0 if we had time. So that's all for today. So at the beginning of the next lecture, we deduce that the functor K0 is homotopy invariant, which is quite useful. Thank you.